Welcome to lecture number 100 of Digital Electronics Circuits. In lecture number 97, 98 and 99, we were dealing with design of synchronous counters. In this lecture, what I am going to explain is how to check whether a given counter is self-starting. That means after designing the counter, how to check whether it is self-starting. If it is not self-starting, how to make it self-starting. Okay. So the concept here is self-starting concept. Okay. Self-starting concept. Now, to just have a brief about this self-starting concept. Suppose you need a counter which is counting a sequence 0, 3, 5, 6, 7, again 0, 3, 5, 6, 7, etc. See, there are invalid states here. The invalid states are 1, 2, 3, 4. Yeah, 1, 2, 4 are the invalid states here. Okay. Now, once the counter enters to these invalid states 1, 2 or 4, if the counter enters to this invalid state, then if it comes back to any of the valid states, in one clock pulse, in one or two clock pulses, then we can say that the given counter is self-starting. Okay. So here 1, 2, 4 are the invalid states, and these states, that is 0, 3, 5, 6, 7 are valid states. Okay. That means if the counter enters to some invalid states like 1, 2, 4, etc., if it is not coming back to 0, or if it is not coming back to 3 or 5 in 1, 2 or 3 clock pulses, you can say that if it is not coming into the valid state, we can say that the counter is not self-starting. Whereas if it is automatically coming back to that valid state, then we can say that the counter is self-starting. Okay. So I will give the example of this self-starting in this lecture. Now coming into lockout condition. So what is meant by lockout? See, once the counter enters an invalid state, and if by applying clock pulses, it is not coming back to any of the valid states, then you can say that the counter is suffering from lockout condition. That is, in general, what you can say is that when the counter is encountered with some invalid states, and if it is unable to come out of that invalid states to any of the valid states, then such kind of situation is known as lockout condition. Okay. Now, to avoid lockout, there are two ways. One is make the counter self-starting, or second method is if invalid state encounters, then reset the counter. That is clear the counter. Okay. So that are the two ways to avoid lockout. Okay. Now let me go with the example. So the question is, design a counter which counts 0356, number 0356, etc. and check whether the counter is self-starting. Counter is self-starting. Okay. That is the question. Okay. Now, what is the step 1? I am choosing a flip-flop. Let me choose P flip-flop. That is the easier one. Okay. Now, second step is draw the excitation table of T flip-flop. This if T present state, next state 0 on. Okay. If present state is okay, if T is equal to 0, whatever is the present state, it will come as next state. If T is equal to 1, whatever is the present state, the complement of that will come in the next state. Okay. So that is basically the toggle operation. Okay. So that is the basic truth table or excitation table of T flip-flop. Okay. Now, here which are the states? Step 3. Which are the states here? The valid states are 0, 3, 5 and 6. So what is the decimal equivalent of 6, or what is the what is the binary equivalent of 6? Binary equivalent of 6, it is 110. So there are 3 bits. This is basically 3 bits. So this is basically, so you need number of flip-flops. Number of flip-flops, that is equal to 3. This is one way of determining number of flip-flops. Or we can write capital N should be less than or equal to 2 raised to n. So here what is the maximum count? Maximum count is 6. So 6 should be less than or equal to 2 raised to n. So what is n? So the possibility of n is 3. You can have 4, but you should choose the minimum value of n. You choose the minimum value of n. Possibility is there for 4, but you should choose the minimum value of n which is applicable. Okay. Now coming into this design. Coming into step 4, I am drawing the state diagram. So which are the valid states I am having? Valid states are 0, 3, 5, 6. Again 0, 3, 5, 6. It will go like that, right? 0, 3, 5, 6, 0, 3, 5, 6 like that. So first is 0. That is 0, 0, 0. That is 0. Next state is 3. 3 is 0, 1, 1. That is 3. Then comes 5. 5 is 1, 0, 1. That is 5. Then comes 6. 6 is 1, 1, 0. Then comes 0. Okay. So this is the basic state diagram. Now let me go with the design of T flip-flop. Okay. So I am having only 4 states. So I am drawing the excitation table here itself. Excitation table. So this is step 5. Okay. So first you have the present state. Present state I am taking as Q3, Q2, Q1. Next state is Q3, Q2, Q1. So what you have is T3, T2 and T1. So present state can be 0, 0, 0. Then comes 0, 0, 0. Then next one is 0, 1, 1. Then 1, 0, 1. 1, 1, 0 and 0, 0, 0. 1, 1, 0. That is sufficient. Okay. Now coming into next state. If it is 0, 0, 0, next state is 0, 1, 1. Okay. Then if it is 0, 1, 1, next state is 1, 0, 1. If it is 1, 0, 1, next state is 1, 1, 0. If it is 1, 1, 0, next state is 0, 0, 0. Now let me write t. Okay. So here I am not taking the entire values. Okay, I am taking only the valid states. 0 to 0, Q3. The variation of Q3 is from 0 to 0. 0 to 0 is 0. 0 to 1, 1. 1 to 1, 0. 1 to 0, it is 1. That is T3. Now what is T2? 0 to 1, 1. 1 to 0, 1. 0 to 1, toggling is here, that is 1. 1 to 0, that is 1. So T2 is entirely 1. Now what is T1? 0 to 1, 1. 1 to 1, 0. 1 to 0, 1. 0 to 0, it is 0. So that is T3, T2 and T1. Now coming into the expressions of this T3, T2 and T1. Okay. So we are having 0, 3, 5, 6 already as a valid state. So I am going to find the expression for T3. T3 in terms of Q3, Q2 and Q1. So if you are writing the decimal equivalence, 0, 0, 0, this is 0, this is 3, this is 5 and this is 6. All other states are invalid. So I am drawing a K-map here, a 3-variable K-map. So this is Q3, Q2, Q1, 1, 2, 3. So this is 0, 1, 0, 0, 0, 1, 1, 1, 1, 0. So I am having 0, 1, 2, 3, 4, 5, 6 and 7. So how to write the values? At 0 it is 0. At 0 it is 0. At 3 it is 1. At 5 it is 0. At 6 it is T3 is 1. Okay. All others you can keep it as don't care. All others you can keep it as don't care. So what we can do? Now here we can club these 4. We can club these 4. If you are clubbing these 4, what is remaining? Here we are having Q2, Q1. This is Q2, Q1 bar. This is Q3 bar and Q3. So what is common? Only Q2 is common. So we can write T3 is equal to Q2. So we can write T3 is equal to Q2 here. Okay. Now coming into T2. Okay. T2 all elements are 1. So we can make T2 as is equal to 1 directly. Because all elements are 1 and all other elements apart from 0, 3, 5 and 6 becomes don't care. Therefore we can take T2 as 1. Now coming to expression for T1. T1 also I am drawing a 3-variable K-map. One, 2, 3. So here I am having Q3, Q2, Q1, 0, 0, 0, 1, 1, 1, 1, 0, 0 and 1. So this is 0, 1, 2, 3, 4, 5, 6 and 7. Okay. So when it is 0, T1 is 1. 0 means T1 is 1. 3 it is 0. 5 it is 1. 6 it is 0. All others are don't care. Okay. So what I can do? So we can club these 4. We can club these 4. So what is common? Yeah, this is Q2 bar Q1. This is Q2 bar Q1 bar. This is Q2 bar Q1. So what is already common factor? The already common factor is Q2 bar. Therefore we can write T1 is equal to Q2 bar. That is the already common factor here. Okay. Now you got T3 is equal to Q2. So what is the expression we have got? T3 is equal to Q2. Then T2 is equal to 1. T2 is equal to 1. And T1 is equal to Q2 bar. T1 is equal to Q2 bar. Now how to draw the circuit? First you can draw T3. T3, that is you are having Q3 and Q3 bar. There is a clock. Then next is T2. T2, Q2 and Q2 bar. Okay. Clock is there. Then comes T1. T1, you are having Q1 and Q1 bar. Now clock signal is common to all these three. Clock signal is common. Okay. Now what is T3? T3 is equal to Q2. So you can draw like this. T3 is equal to Q2. Then T2 is equal to 1. T2 is equal to 1. What is T1? T1 is equal to Q2 bar. So we can write T1 is equal to Q2 bar. So what are the outputs? Q3 is an output. Q2 is an output. Q1 is also an output. And you can have preset here. You can sort these four and make that as this is preset. Now coming into clear, you are having clear pin here also. Okay, you can sort this. So there we are having clear. Okay, so that is the logic circuit for this counter. Now we need to check whether it is self-static. Okay, so the question was we need to check whether the given counter is self-static. So next step is checking for self-static. Checking for self-starting. Okay. So here which are the valid states? The valid states are 0, 3, 5 and 6. Which are the invalid states then? The invalid states are 1, 2, 3, 4 and 7. Since this is 3-bit, you are having 1, 2, 4 and 7 are the invalid states. Because it is only 3-bit, you can have 1, 2, 4 and 7. That are the invalid states. Now, if it encounters with an invalid state, what happens? That is the question. So, what I am having is the expression of what? How to check? Yeah. So, I am writing the invalid states here. That is Q3, Q2, Q1. Then, what happens to T3, T2 and T1? So this is the present state. This is T3, T2 and T1. What will be the next state? Okay. Next state is Q3, Q2, Q1. What happens? Okay. So 1 becomes 0, 0, 1. 2 is 0, 1, 0. 4 is 1, 0, 0. 7 is 1, 1, 1. Okay. So I have written the invalid states. So this is 0, 1, 2. So 0, 1, 2, 0, 1, 4, 7. Sorry. There is a mistake. The invalid states are 1, 2, 4 and 7. These are the invalid states. So what is T3? What we are having the expression of T3? T3 you can write it as T3 is Q2. And then next one T2 is 1. T2 is equal to 1. Then what we have? T1 is equal to Q2 bar. T1 is equal to Q2 bar. Okay, that is based on present state. So T3 is equal to Q2 directly. So it is 0, 1, 0, 1. What is T2? T2 is 1. What is T1? T1 is Q2 bar. So it is 0 becomes 1. 1 becomes 0. 0 becomes 1. 1 becomes 0. Okay. Now let us see what happens. Here T3 is 0. Okay. 0 is initial state. If T3 is 0, so 0 means it will become no change. 1 means there is change. That means 0 will be changed to 1. 1, 0. That means no change. That means 1 will change to 1 itself. 1, 1. That means 1 will be toggled to 0. Now what is Q2? 0, 1. 1 means there is toggle. So 0, 1 means T2, 1 means Q2 will be toggled. Okay, so T2 all values are 1. That means the values of Q2 will be toggled. So 0 will become 1. 1 will become 0. 0 will become 1. 1 will become 0. Right? So T2, that is ready. Now coming into T1. 1, 1. 1 means Q1, present state is 1, toggle is 1. That means present in the next state it will become 0. Now 0, 0. Now change, so it is 0. 0, 1. That means that is changes, that is 1. 1, 0. 1, 0, what happens? Yeah. 1, 1, 0 means the present state will remain. That is 1. Now if you are looking into the decimal numbers here, what happens? 0, 1, 0. 0, 1, 0, it is 2. 1, 0, 0, it is 4. 1, 1, 1, it is 7. 0, 0, 1, it is 1. So what happens? Even if we are having the present state, these are the invalid states. With the present design, it is again going into invalid state. The present design, it is again going into invalid state. Therefore, what I can say, the present design suffers from lockout condition. That is the counter is not self-starting. The counter is not self-starting. Okay. So that is the conclusion from here. Now, how to eliminate this lockout? That is the next question. Okay. Now see, here you got that the counter itself is not self-starting, and I have explained the lockout condition. So lockout condition means from the invalid state it is going into another invalid state. Okay. So that means it is not coming back to any of the valid states. That means the counter is not self-starting. Now how to make the counter self-starting? That is next question. Okay. So there are two ways. Okay. So the two ways of self-starting is that if the counter is going into any invalid state, you can make it into a reset condition. That is the first condition. Or you can add the invalid states and make the next state as one of the valid states. Okay. So that is two ways. Okay. So there are to eliminate lockout, or to make the counter self-starting, or to make the counter self-starting. Two ways are there. Okay. One is you can reset when invalid state encounters. Or second method is account for invalid states in such a way that when invalid state comes, make next state as a valid state. There are two methods. So here I will explain both the methods in this lecture, and from the next lecture I will do with some other techniques. Okay, or some other technique means I will do either reset or account for invalid states. So first of all I need to reset. Reset means I need to reset back to 0. Okay, 0 is a valid state, so I can reset it. So which are the invalid states? So method 1 is resetting the counter. Okay. So which are the invalid states? Invalid states are 0. What are the invalid states? Invalid states are 1, 2, 4, 7. Invalid states are 1, 2, 4 and 7. If these states encounters, make a reset as 0, as 1. Make reset as 1. So, what are the states? That is Q3, Q2, Q1. We give a reset. So, 1. 1 means 0, 0, 1. 2 means 0, 1, 0. 4 means 1, 0, 0. 7 means 1, 1, 1. So, in all these cases, make reset as 1. Therefore, reset we can write it as Q3 bar, Q2 bar, Q1, or Q3 bar, Q2, Q1 bar, or Q3, Q2 bar, Q1 bar, or Q3, Q2, Q1. You can write in this form. Okay. Now, yeah. Okay. So you can make the reset like this. Reset is Q3 bar, Q2 bar, Q1, or Q3 bar, Q2, Q1 bar, or Q3, Q2 bar, Q1 bar, or Q3, Q2, Q1. Okay. You can make in this form. Okay. And you can form the reset. So how to form the reset then? Okay. So that is the next question. So I will draw that circuit again. So we are having T3, Q3, Q3 bar. Here I am having T2, T2, Q2, Q2 bar. Then I am having T1, T1. We are having Q1 and Q1 bar. Okay. Now, okay. Now, if you are combining these two terms, okay. So before going into that, let me simplify it. Let me simplify that term. Okay. Before going into the circuit, let me simplify that term. Just okay. So R we can write it as, if you are taking these two terms, okay. Right, Q3 bar, Q2 bar, Q1, Q1 bar. Sorry. So if you are taking these two terms, that means, yeah, this one and this one. What will I get? Q1 bar is common. So Q1 bar and Q3 bar, Q2, or Q3, Q2 bar. Okay. Now, if I am taking these two terms, which is common, Q1 is common. So you can write or Q1 and Q3 bar, Q2 bar, or Q3, Q2. So what is it? That is Q1 bar into what is this? This is Q3 XOR Q2, or Q1 XNOR Q1 and Q3 XNOR Q2. So Q3 XNOR Q2. So this is like A bar B or A B bar. So you can write it as Q1 XOR Q3 XOR Q2. That is a simplification. So that is reset. Reset is Q1 XOR Q3 XOR Q2. I have just simplified it. Now let me redraw the circuit. So we are having T3. This is T3, Q3, Q3 bar. We are having a clock. Now comes to T2, T2, Q2, Q2 bar. Then comes T1, T1, that is Q1, Q1 bar. Clock is there, clock is common. Clock is common here. Okay. Now what is T3? So T3 it is Q2. T3 is Q2. T3 comes as Q2, right? T3 is Q2. Then T2 is 1. T2 is 1. And what is T1? T1 is Q2 bar. T1 is Q2 bar. Now here we are having clear pins, right? Clear clear, clear. So take that clear pins out. Okay. And what is reset? Reset is Q3 XOR with Q2, Q3 XOR Q2 XOR with Q1, right? So that's the Q1. Okay. So you can have like this. These two things are XORed. These two is XORed, and that result is XORed with Q1. Okay. And you can give, if it is clear bar here, you should give it as not. And if you are writing clear, you can give directly. If it is clear bar, you can give it directly. It is clear, you can give it as direct, and that is standard to here. That means this is the reset. When reset is equal to 1, all the flip-flops are getting resetted. Here you are having preset. Okay. This is preset, preset, preset. Okay. So you can make preset here. Okay. And you can convert it into a single thing, that is preset. Okay. So here what happens to clear? Clear is basically on reset pin. Okay. So this is one method of avoiding lockout or making the counter self-starting. Okay. Now coming into method 2. In method 2, what I am going to do is, if an invalid state encounters, then the next state we are making it into a valid state. So making it into a valid state. So let me draw a state diagram for that. Okay. Drawing the state diagram. So here which are the valid states? The valid states are 0, it is 0, 3, 5, 6. 0, 3, 5, 6 are the valid states. That is 0, 0, 0, 0, 1, 1, 5 is 1, 0, 1, 6 is 1, 1, 0. Okay. This is 0, 3, 5, 6. So what are the invalid states? Invalid states are 1 is an invalid state. 1 means it is 0, 0, 1. Okay. If this 1 arises, you can make it in the next state, you can go to 0, 0, 0. No problem. Next one is 2. 2 is what? 0, 1, 0. That is 2. Then also you can make the next state as 0. No problem. Now 4 is an invalid state. Okay. If 4 is an invalid state, you can make it into 5. Okay. No problem. 1, 0, 0, that is 4. Next state you can go to some valid state, that is 5. Now 6 is also an invalid state. Sorry, 6 is 7. 7 is a 0, 3, 5, 6. Now 7 is an invalid state. Okay. If 7 is an invalid state, it can go to where? 7 means it can go to 0, or it can go to 5, or it can go to 3, or it can go to 6. So, but for easiness, I am making it into 0. 7 means it is 1, 1, 1. That is 7. If it is 7 also, I am making it into go to 0. Okay. So, based on this state diagram, I am going to draw the excitation table. Okay. So, here I am having what? Present state, next state, T3, T2, T1. So what do you have? Q3, Q2, Q1. Next state is Q3, Q2, Q1. So you can write from 0 to 7 directly. So 0, 1, 2, 3, 4, 5, 6, and 7. So what is this? This is 0, 1, 2, 3, 4, 5, 6, and 7. That is the present state. Now coming into the next state. Okay. If it is 0, next state is 3. So it is 0, 1, 1. If it is 1, next state is 0. Okay. If it is 2, what is 2? 2, the next state is 0. Okay. If it is 3, next state is 5. So it is 1, 0, 1. If it is 4, what is the next state? Next state, we have make it into 5. So 1, 0, 0, next state is 5. That is 1, 0, 1. Now, when it is 5, next state is 6. That is 1, 1, 0. If it is 6, next state is 0, 0, 0. And if it is 7 also, we are making it into 0, 0, 0. Okay. Now you rewrite T3, T2 and T1. Okay. Now coming into what is T3? 0 to 0, 0. 0 to 0, 0. 0 to 0, 0. 0 to 1, 1. 1 to 1, 0. 1 to 1, 0. 1 to 0, 1. 1 to 0, it is 1. Now what is T2? 0 to 1 is 1. 0 to 0, 0. 1 to 0, 1. 1 to 0, 1. 0 to 0, 0. 0 to 1, 1. 1 to 0, 1. 1 to 0, 1. Now what is T1? 0 to 1, 1. 1 to 0, 1. 0 to 0, 0. 1 to 1, 0. 0 to 1, 1. 1 to 0, 1. 0 to 0, 0. 1 to 0, it is 1. Now you need to derive the expressions for T3, T2 and T1. Now let me derive the expressions for T3, T2 and T1. To find the expression for T3, I am having a 3-variable K-map. 1, 2, 3. So here I am having, this is Q3, Q2, Q1, 0, 0, 0, 1, 1, 1, 1, 0, 0, 1. This is 0, 1, 2, 3, 4, 5, 6 and 7. For 0, 0, 1, 2, it is 0, 0, 0. 0, 1, 2, then 3, 4, 5, 1 double 0, 3, 4, 5, then 6, 7 it is 1. For 6 and 7 it is 1. Now how will you club? You can club these two. If I am clubbing these two, what is the expression? It is Q2, Q1. So, and you can club these two. If you are clubbing these two, what is the expression? This is Q3, Q3, Q2, right? It is Q3, Q2. Okay. Therefore, we can write T3 as Q2, Q1 or Q3, Q2. That is T3. Now coming into expression of T2, again you are having a 3-variable K-map. Having a 3-variable K-map. So this is Q3, Q2, Q1, 0, 1, 0, 0, 0, 1, 1, 1, 1, 0. So here I am having 0, 1, 2, 3, 4, 5, 6 and 7. So coming back to T2. T2 it is 1, 0, double 1. 1, 0, double 1. Then coming into 4, 5, 6, 7. 0, double 1. 0, 5, 6, 7. Okay. Now how can I club? That is the next question. So here I can club like this. I can club these 4, right? If I am clubbing these 4, what will I get? If I am clubbing these 4, what is the only common factor? That is Q2. So I am having the common factor as Q2. Next thing is I can club these 2. If I am clubbing these 2, what is common? I am having Q3 is common there, along with what? Along with the Q1. Along with the Q1. That is Q3, Q1. Then I can club this one and this one. Okay. So I am clubbing that elements which is common. Q3 bar is common, and here Q1 bar is common. So that is Q3 bar, Q1 bar. Therefore we can write T2 is equal to Q2 or Q3 Q1 or Q3 bar Q1 bar. Okay. That we can write it as Q2 or Q3 H nor Q1. Q2 or Q3 H nor Q1. That is T2. Now coming into T1. T1 under 3 variable K-map. And coming into T1. 1, 2, 3. This is Q3, Q2, Q1. 0, 0, 0, 1, 1, 1, 1, 0. This is 0, 1, 0, 1, 2, 3, 4, 5, 6, and 7. How will it look like? It is 1, 1, 1, 0, 0. 1, 1, 0. Then 1, 1, 0, 1. 1, 1, 0, and 1. Now how will I club? Now I can club these 4. If I am clubbing these 4, what is common? Q2 bar is common, right? So this is Q2 bar. Then I can club these 2. If I am clubbing these 2, what is common? Q3 is common along with this Q2. So that is Q3, Q2. Therefore we can write T1 as Q2 bar or Q3, Q2. Now what is T2? Right here, what is T2? T2 is Q2 or Q3 X nor Q1. Now what is T1? T3. What is T3? T3 is equal to Q2 Q1 Q2 Q1 or Q3 Q2. Now let me draw the logic circuit for this. If I am drawing the logic circuit, I am having T3 Q3 Q3 bar. This is T2 Q2 Q2 bar. Now here what I am having is T1, this Q1 Q1 bar. Now what is T3? T3 is Q2 Q1 Q2 Q1 or Q3 Q2. We can write it as Q3 Q2 and gate. Now here you should give an OR gate. This is an OR gate and you should give it to T3. Okay. So that is T3. Now what is T2? T2 is Q2 or Q3. Q3 is here. Yeah. This is this is Q3. Q3 X nor with the Q1. This is X nor with the Q1, right? Okay. These two things are odd. These two things are odd and given to T2. Okay. Now what is T1? T1 is Q2 bar. T1 is Q2 bar is here or Q3 Q2. Already Q3 Q2 is coming in here. This is Q3 Q2. I can take from there. Q3 Q2 is coming here. And I am taking in that OR here and giving it into T1. And clock is common. There is a common clock that is coming in. This clock. Clock is going in here. a common clock, and preset you can give separately. This is preset. This you can give a preset here, no problem. Now coming into clear. This is clear, and this is clear. Okay. So this is how you are redesigning the circuit to avoid lockout. Okay. So in this lecture, what I have dealt is basically a counter which is going to count the states 0, 3, 5, 6, and I have checked whether the counter is self-starting, and we have found that the counter is not self-starting because it is from one invalid state it is jumping into next invalid state. And we have now to eliminate this lockout or to eliminate this not self-starting condition, we have made it into we have resetted it. We have avoided this lockout condition or avoided this not self-starting condition using two methods. One is by resetting the counter. This is a pretty easy way, or including the invalid states in the excitation table and making the next state as one of the valid states. Okay, and we have redesigned the counter. Okay, so that two are the methods which is being followed. Okay, so I think you have got a fair idea about what is meant by lockout, or what is meant by lockout condition, what is meant by self-starting condition, everything, and what is meant by not self-starting. Okay, so thank you, and in the next lecture we will deal with some other counters. Thank you.